here. So hopefully you guys can hear me okay. Yeah, my guess is people are sleeping in, and or I've heard there's a chemistry midterm this week. So hope that's not why people are missing class, because if you miss one class for a midterm in another class, things can pile up a bit. But anyway, so one thing I wanted to do was talk a little bit about the test on Friday. I know it was a little on the hard side. I'm sorry about that. Sometimes it's hard to gauge exactly the right difficulty level. But one thing I wanted to say was to not panic too much, that I realize the testing online is difficult for everybody, and I'm going to do my best to make sure, I'm going to definitely ensure that the grade distribution, the mean and everything in this class is the same as what I typically have when I teach the class online. So if that means scaling everything up, then that's what it means. I don't know, one of the TAs is marking the written part right now. There's 350 papers for her to mark, so I'm not sure how long it's going to take. So I'm hoping to have the marks finished by Friday. Okay. Also, I wanted to talk a little bit, somebody was asking about what the grades on the first test mean, and so I thought that we could look at that. So I'm going to switch over now to my slideshow here. Okay, so now we're into PowerPoint. So this is just some rough estimates for the grades here for the first test, just to give you an idea of what the grade distribution looked like. It was a very broad distribution. It was kind of unusual, but I think that's because we're all getting used to these online tests. So basically, so you can see the way this works is if your grade is somewhere between a 14.5 and a 17 out of 17, remember it was 9 points for the Canvas quiz and then 8 points for the written part. So you add that together, you get 17 as a total. Okay. So then your grade estimate would be an A. Okay, and 104 students, so almost a third of the class got an A on that first test. Okay, and then you can see how it breaks down as you go. All right. So you can figure out roughly what your grade on that test means. Okay, this is sort of an estimate of what that grade would be, okay, for the different ranges of points. Okay, and so very few people failed. Not a lot of people tend to fail this class. You really have to do very poorly, but not everybody's going to get an A either. Okay, so your marks are all in Canvas. I think the people typically did better on this test, the first test, but I don't know for sure yet because we haven't seen the marks for the test 2. Okay, people did better on the Canvas quiz, definitely for test 1. Okay, so, but like I said, we don't know for sure, so we'll have to wait and see what things look like. Okay, so that's our rough guesstimates of the grades. So now we're going to go on and talk about some physics. All right, so the last thing we were talking about was a quantity called the moment of inertia, which is essentially, it's that big capital I that shows up in our formula for rotational kinetic energy of a rigid object. And what I is it essentially tells you how hard it is to rotate an object. Okay, it acts like a mass. And we're going to see it act like a mass again when we look at the rotational equivalent of force, which is known as torque, in our next lecture. Okay, and we saw that if you wanted to calculate the moment of inertia for a collection of point masses, MI, it would be the sum of each of the individual point masses, MI, multiplied by the distance those point masses are from the axis about which you're rotating. Okay, so it would be MI/RI squared. Okay, so that's how you do it if you have a collection of point masses. If you have a continuous object, all right, then you would turn that sum into an integral that looks something like this. You would integrate r² over the whole mass of the object. So that's an integral you can do if you know some calculus. We're not actually going to do that integral in this class, but I thought I would show you what it looked like. Some of you may run into that in a later class. Okay, and so if you were to do this integral for various different shaped objects, then you get results that look like this. Okay, so here are the moments of inertia for various solid objects about axes. In most of these cases, the axis is through the center of mass. So you've got a solid sphere through its center, which is 2/5 mr squared, a solid cylinder through its center. Remember, sometimes they call it a cylinder and sometimes they call it a disk. They usually call it a disk if it's wider than it is tall, and a cylinder if it's taller than it is wide. A thin rod, okay, we have here through its center, and this is a cylindrical rod, but it doesn't have to be, it could be a stick of any kind, it could be rectangular in shape. A thin spherical shell, so that's a sphere, it's like an empty ball, a hollow ball, essentially. So a sphere with an empty center, a thin cylindrical shell or a ring. And notice for a thin cylindrical shell or a ring, it's like you have a single mass m at a distance r from the axis, because all of the mass is at a distance r from the axis. Okay? And then the only one that's not through the center here is the last one, which is a thin rod about one end. And notice that the thin rod about one end is a bigger result, 1/3 ml squared, than the thin rod about its center. It's harder to rotate a rod about its end than about its center because there's more mass further away from the axis. And so that's why you get a bigger result there. Okay, and so if you need these formulas, then you may need these formulas. I typically, depends on the problem, but sometimes I will give it to you, but if not, it's probably good to have it on your formula sheet just in case. So I thought we would do a clicker question, a poll question here. So let's start the poll going on moments of inertia. So now you can think about the formulas here, but you can probably figure this one out just conceptually thinking about where the mass is located for this one. Okay, and so the question is, so you have two spheres, they have the same radius and the same mass. One is made of solid aluminum and the other is made from a hollow shell of gold. And the question is, which one has the bigger moment of inertia about an axis through its center? So you got solid aluminum, hollow gold, or they would both have the same moment of inertia. So like I said, you can either try and use the formulas, but in this case, you can also think about where is the mass located and how far is the mass from the axis. Because remember, the further the mass is from the axis, the bigger the moment of inertia will be. All right, I think maybe we'll do about 10 more seconds here. All right, so if you're not sure, go ahead and guess. All right, 5, 4, 3, 2, 1. Okay, it looks like everybody's pretty much had a chance to guess, so let's look at the answers. So what do we see? Okay, so the largest group thinks that the answer is hollow gold. Okay, but then we have some votes both for solid aluminum and some votes for that they would have the same moment of inertia. So let's have a look at how you would figure this out. Okay, so like I was saying, the main thing to remember is that moment inertia depends on the mass and its distance from the axis squared. Okay, this will be bigger for the shell since its mass is located further from the axis on average, right? With the solid object, some of the mass is really close to the axis and some is far away. But for the shell, okay, all of the mass would be further away, and so that makes your answer the hollow gold. Okay, so that's how it works. Okay, that's how moment of inertia works. So any questions on how that works? Okay, it looks like there are questions on other things, but not on how that works. Okay, so we're going to move on then to one of the next topics in the pre-lecture, which was something called the parallel axis theorem. Now, this is a useful theorem for when you know the moment of inertia about the center of mass and you're trying to figure out the moment of inertia about another axis. Okay, and so the idea is that the moment of inertia about an axis that's parallel to an axis through the center of mass is just equal to the moment of inertia about the center of mass plus the total mass, big M, remember big M is the total mass here, times the distance, that perpendicular distance between the two axes, h squared. Okay, so I thought I would try to show you how this worked, that we would actually do one of these calculations here. So we are going to go back. You might remember this from our last lecture, this configuration. So this was a configuration of 3-point masses with very thin rods, and we ignored the masses of the rods. Okay, so and so what we're going to do now is try to figure out a couple of different things. First, we're going to figure out where the x position of the center of mass is. We didn't do that last time. Last time we just figured out, you might remember, the moment of inertia about the x-axis and the moment of inertia about the y-axis. And then we're going to try to figure out what is the I about the center of mass, okay, along an axis through the x center of mass is what we're going to try and do. All right, and so I'm hoping that my document camera is going to work this time. It wasn't behaving before, so let me just have a quick look and see if it's still misbehaving. Yes, it's still, for some reason, it's flipped itself. So I'm going to try something different here. Let's see if this works. Okay, it is not behaving. That's not good. All right, let me try one more time. All right, I'm going to try one more thing to see if I can get my document camera to work. Otherwise, we're going to have to skip this. Which is I'm going to unplug it. And plug it back in again. Okay, my document camera is still not working, and I'm not sure why. All right, I guess we're going to have to skip that for today. What I will do then is I'm going to just have to post the calculation for this one for you guys. And hopefully, if we have time next time, I can show you how to do this one. I really apologize that my document camera has decided to reverse everything. Yeah, so I'll work through the problem and I'll post it for you guys later. And I apologize that it's not behaving. Okay. I'm just trying to think if there's something else I can do. If there's time at the end, okay, I'll see if I can get my my iPad working. So, and we'll give that a try. Okay. All right. In the meantime, we're going to go on and we'll try and do that at the end. Okay. So we will try that at the end. So the next topic we are going to talk about is rolling. All right. So when an object rolls without slipping, which means it makes perfect contact with the surface as it rolls, okay, then the velocity of the center of mass of the object, so how fast the center of mass is moving along parallel to the surface, is equal to the radius of the rolling object times the angular velocity omega. Okay, and in this case, you can see the object is rolling and it's got, again, this is the magnitude of the omega, because in this case, from our view, it's moving clockwise, right? Okay. So, so technically, from this view, it would be a negative omega, but we're talking about the magnitude of the velocity of the center of mass. Okay, so in most of these formulas, you're talking about the magnitude of the angular velocity here. Okay, so what does that mean? Well, that means if you have an object that's both rotating and translating, then it has two kinds of kinetic energy. So it has both your translational kinetic energy, 1/2 the mass times the velocity of the center of mass squared, and it has the rotational kinetic energy, which is 1/2 the moment of inertia about the center of mass times your omega squared, your angular velocity squared. Okay, and so some amount of energy is going to be in the object translating, and some amount of energy is going to be in the object rotating, and how much is in each part, all right, is going to depend on how big that I center of mass is. So in the pre-lecture, they were looking at an object rolling down an inclined plane. This is a sort of a classic rolling example. And it starts, so you have a rolling object, a circular cross-section object of some kind, and it starts at the top of the ramp at some height h. At rest, so it's not rotating or translating, and then at some time later, so it rolls down the ramp, okay, and at some time later, we want to figure out how fast is it moving. So what's the velocity about the center of mass, okay, that translational velocity when it gets to the bottom. All right, so what they found out in the pre-lecture was that the moment of inertia for a sphere, say you do this for a sphere, that's the one they did in the pre-lecture. We know the moment of inertia of a sphere about its center of mass is 2/5 mr squared, and they showed that the velocity about the center of mass was equal to the square root of 10/7 times the acceleration due to gravity times the height you start at. So the interesting things to notice here is the answer doesn't depend on the mass of the object. It doesn't depend on the radius of the object. All it depends on is the acceleration due to gravity, so which planet you're on, and how high the ramp is, what height you begin. Okay, because you can imagine, because it basically starts with a certain amount of gravitational potential energy, and that gravitational potential energy gets converted into your two different kinds of kinetic energy, your rotational and your translational. Okay, so now, what if you had a disk instead of a sphere? So what do we know about a disk? We know that the moment of inertia for a disk, remember a disk is a flat cylinder, is 1/2 mr squared. So for the same mass and the same r, that's a bigger moment of inertia, right? So 1/2 is bigger than 2/5. So my question for you here is, how do you think the velocity of the center of mass is going to compare? for a disk? Do you think it's going to be bigger or smaller than the velocity for the sphere? Anyone have a guess? Okay, so we've got a bigger, a smaller, we got a same, we got a mixture of answers, same. Okay, so it turns out that it's smaller. So everybody who guessed smaller was right. Okay, if you go through the same calculation they did in the pre-lecture, but instead of plugging in 2/5 mr squared, you plug in 1/2 mr squared, you'll get a velocity of the center of mass, prime, though this is for the disk, of 4/3, square root of 4/3 times GH, which is smaller. Okay, 4/3 is smaller, just slightly smaller than 10/7. Okay, so so the disk has a smaller velocity, is moving more slowly at the bottom. Okay, and so essentially what's happening, okay, is the larger the moment of inertia is, the smaller the velocity at the bottom of the ramp will be. So this is specific for an object rolling down a ramp like this of a given height. Okay, and basically what's going on is the larger the I, the larger the moment of inertia, the more of the kinetic energy has to go into rotation, and the less, okay, then goes into translation. All right, though of course they're linked to each other. So what I thought we would do is do another poll question on this. So we'll go back to our polling. Okay, so what's our question? Our question is, so we have a cylindrical disk, which has an I of 1/2 mr squared, and we have a ring now, which has an I of mr squared. They have the same radius, and they start at rest at the top of an incline. They're released at the same time. And the question is, so they both roll without slipping. Okay, we'll only do rolling without slipping in this class. We won't do the other kind of rolling. And the question is, which one reaches the bottom of the ramp first? So they're having a race, and you want to know which one wins the race. And I'm going to try and fix my document camera while you guys are guessing. Okay, I think maybe we'll do 10 more seconds here. So if you're not sure, go ahead and guess. All right, 5, 4, 3, 2, 1. So let's have a look at the responses. All right, so what do we have? We have the biggest group is voting for A, okay, that the disk is going to win. All right, and the next group is voting for B, the next largest group, the ring's going to win. Okay, so people think maybe the disk has an advantage over the ring. Okay, and then what do we have left? We have that also a few votes for that they reach the bottom at the same time. All right, so what I thought, so let's discuss it, and then I'm going to actually show you it, okay, in case you don't believe it. So the answer is the disk will win. Okay, the disk will reach the bottom first because it has a smaller moment of inertia, right, relatively, 1/2 mr squared. Okay, it turns out the mass doesn't actually matter. So even though, and the radius doesn't matter for that matter. Okay, so what matters is the moment of inertia. Okay, so a smaller I, as we saw, leads to a larger velocity about through the center of mass, right? That translational velocity will be larger, which means a larger average velocity for the whole trip, okay, which means the disk should win. Okay, so the solid one as opposed to the hollow one will win. And so I found this video, and hopefully this is going to work for you guys. So I found this one on YouTube because I don't have a good video of me doing this. And this video kind of cracks me up because I think if you were to ask somebody to picture a physics professor, this is what a lot of people would picture, is this guy with his tie. Okay, so anyway, so I'm going to play this. I don't know how well you're going to be able to hear the sound, but let's give it a try. You don't necessarily need to hear the sound, but basically you can see he's got a disk and he's got a ring, and he's going to do this experiment for us. So let's see if this works for us.
We're going to release both of these from rest at the top of this inclined plane and ask which one of them wins the trip to the bottom. Will it be the one with the larger moment of inertia, mr squared, or the one with the smaller moment of inertia, 1/2 mr squared? So as you can see, the winner is the one with the smaller moment of inertia. Why is that? And the reason is that it has less resistance to turning motion because it has a smaller moment of inertia. So moment of inertia acts a lot like, moment of inertia for rotational motion acts a lot like mass for translational motion. The bigger the mass, the slower it is to start up. The bigger the moment of inertia, the slower it is to start turning. That's moment of inertia.
So there we go. So you can see how that works. So any questions about that? I'm glad the sound worked for you guys on that one. We also had the captioning, which is nice. So, so you can see how that depends on our moment of inertia. So now we're going to start talking about rotational kinematics. So we did a whole multiple chapters on translational or linear kinematics. First we did one-dimensional, and then we did two-dimensional. And so now we're going to look at the kinematics for our rotational variables. And you're going to see a lot of similarities. The main difference here is that we're not going to have to worry about vectors or two-dimensional rotations. Okay, we're always going to have a rotation about a single axis and look at what happens about that axis. Okay, so first quantity we have to define is our average angular acceleration. So if you have an object that's rotating, say here's our yellow disk here, and it starts, we're watching this little point with the red X rotate. Okay, and so at time equals 0, the little red X is at the position shown. It has a tangential velocity v0, okay, and it's got an angular velocity omega 0, right? We know it has an angular velocity if it has that tangential velocity v0 there, and then it rotates through some angle delta theta, and at some later time t, it's now spinning with an angular velocity omega, and you can see that point on the rim of the ring now has a larger velocity, larger magnitude velocity, okay, because now the object is spinning faster. So there's been a change in angular velocity, and how do you calculate average angular acceleration? It's just that change in angular velocity, omega minus omega 0, divided by the time elapsed. Okay, so if you then go through and basically apply, or basically what you're doing is translating the variables, okay, going from, say, your one-dimensional kinematic equations, okay, where you have x and v0x and ax, okay, so your x then becomes your basically linear position, x becomes angular position theta, your linear velocity or translational velocity v becomes angular velocity omega, and your acceleration becomes your angular acceleration alpha, and you end up with a set of equations. We get our 3 kinematic equations in terms of theta, omega, and alpha. Okay, and like I said last time, in the pre-lectures, they like to do little subscripts z, because they like to talk about it rotating about the z axis. We'll mostly just ignore those z's because we'll only ever really be looking at rotating about a given axis. So you'll be told which axis we're looking at the rotation about. Okay, all right, but you can see the format is exactly the same. Okay, where you've got, you know, for example, in the first equation, it's final position equals initial position plus initial velocity times time plus 1/2 acceleration times time squared. It's exactly the same format, and the same is true for the other two. Okay, and remember here that just like angular acceleration has units of radians per second squared, we'll have theta in units of radians and omega in units of radians per second. So what I thought we would do now is another poll question here. And we got 3 choices for this one. Okay, so the question is, so we have a potter's wheel, and it's rotating in the clockwise direction as seen from above, so that's our vantage point, okay? The potter steps on the brake and causes the wheel to slow to a stop with a constant deceleration. Okay, so it's slowing down. Which of the following is true for the angular acceleration of the potter's wheel as seen from above? Okay, so will the angular acceleration be positive while the wheel is slowing down? Will the angular acceleration be negative while the wheel is slowing down? Or will it be 0 while the wheel is slowing down? And one thing to remember here is that we did define directions for angular velocity. And remember, angular velocity is positive if you're rotating in the clockwise direction, and it's negative if you're rotating in the clockwise. So positive for counterclockwise, negative for clockwise, angular velocity. And the same rules are going to apply to our angular acceleration, okay, in terms of changes in velocity. Okay, I think we'll do 10 more seconds again. So go ahead and guess if you're not sure. All right, 5, 4, 3, 2, 1. So let's see what so this is actually very fascinating to me because it's a dead heat. Okay, it's a tie between A and B. Oh, no, now we just picked up an extra one for B. Okay, so whether the angular acceleration is positive while the wheel is slowing down or it's negative while the wheel is slowing down. Okay, so so I have a question for you. Let's start with the question is, if something is rotating in the clockwise direction, is the angular velocity positive or negative? Good, it's negative, right. Okay, so if it's so we have something that's rotating, right, with a negative velocity, right? Okay, and it's going from negative to 0. So if you go from negative to 0, is that a positive change or a negative change? Are you becoming more positive? Positive. Yes. Okay. So basically, the answer basically, the initial angular velocity was negative. The final angular velocity is 0. So the change in angular velocity is positive. Basically, final 0 minus initial omega, but omega is negative there. That's a positive quantity. So therefore, remember, angular velocity is angular acceleration is change in angular velocity divided by the time elapsed, right? So if the change in angular velocity is positive, then your angular acceleration must be positive. So the answer was actually A. All right. So that's another case of just being careful with your signs, okay? And remembering that that your acceleration always represents the change in velocity, and its sign, okay, is going to be the same sign, positive or negative in this case. So this is a lot like our one-dimensional motion, right? Okay, where so like in this case, you're moving in the negative direction, but you're slowing down. If you're moving negative but slowing down, that means a positive acceleration. So any other questions about that? So I'm not sure what you mean by is I inversely proportional to W. That I'm not sure what you mean. I mean, are you saying is moment of inertia inversely proportional to so I am going to try now to get my iPad working and see if I can show you that last problem really quickly. See if I can log in here on my iPad really quickly. And at least give you the beginning of that problem. Okay, so let's do that. Okay, so let's see if I can share the whiteboard. All right, so that looks like it's working. I'm hoping you can see the whiteboard okay. All right, so now we're going to go back to our situation for the last couple minutes that looked something like this. Okay, where we had our three masses, our one mass, our other mass, and our other mass, like that. And this was our x-axis, and this was our y-axis. So sorry for the messy writing here. I don't do as well. Okay, and we had a rod like this, and we have a rod like this. Okay, and this one is located at x equals 3.3 meters. And this one up here, okay, I don't remember where that one was located. I think it was 1.8, but we don't actually need that one. Because what we're going to do first is figure out where the x of the center of mass is. All right. Okay, so how do we do that? All right, so we have one mass. The other thing we need to know is the sizes of the masses. This is 1 kilogram. This was 1 kilogram, and this one was 2 kilograms. Those are our masses here. Okay, kilogram, I should write in here. Okay, so how do we figure out the position, the x position of the center of mass? Remember, it's just our weighted average. Okay, so it's going to be 1 kilogram for the first mass times 0, because it's right on the y-axis. Okay, plus 1 kilogram times our 3.3. I'm just going to write the number there because I'm running out of space. Plus, and then 2 kilograms times our 3.3. Okay, that's kind of a mess. Sorry about that. I'm running out of space. And then we're going to divide the whole thing. I will write this up neatly on paper, but I just wanted to show you how it works. Okay, all divided by 4 kilograms. And what do you get? We get x center of mass is equal to 2.475 liters. So it's about here. Okay, that's about where x center of mass is in the x direction. So it's somewhere along this line. All right, and if you think about it, it kind of makes sense. It's closer to the 1 kilogram and 2 kilogram mass, the 3 kilograms on to the right, and further away from the 1 kilogram to the left of it. Okay, so that's how you figure out. So now what we're going to do is we're going to try to figure out, like I said, we're trying to figure out I about the center of mass. All right, and we have to remember our parallel axis formula, which is that I equals I about the center of mass plus m times h squared. Okay, and we happen to already know the moment of inertia about the y-axis. So this I here is about the y-axis. You know that one. Okay, and we know how far this, the x center of mass is, an axis through the center of mass, okay, is, we know our h, which is this distance here. Okay, our h is just our 2.475 meters. That is our h, right? Because that's how far we are from the y-axis. Okay, so, and I just realized you can't see the I there. Okay, so what we're going to do now, I'm going to have to clear this, okay, and so that I can do the rest of the math. Okay, so we're going to start with, we got 2 minutes to do this. I'm going to clear the whole thing. Okay, so we're going to start with our I equals I center of mass plus mh squared. So that means that I center of mass is just I minus mh squared. Okay? And like I said, we found out the I about the y-axis last time. That's 32 point, I'm going to keep an extra sig fig here, 32.67 kilogram meter squared. We found that out last time. And then minus the total mass, which are our 4 kilograms, and then our h squared, which is 2.475 meters squared. And so now you can see we're going to get a smaller number, right? I center of mass is less than I, and that kind of makes sense that the moment of inertia about that center of mass axis, that axis through the center of mass, okay, will be smaller than the moment of inertia about the y-axis, right? Because now the mass is more evenly distributed, right? And what do we get? We get that I center of mass is 8.17 kilogram meter squared. Okay, so that's what the moment of inertia about the center of mass would be using the parallel axis theorem. Now you can also calculate it from scratch. Okay, really quick, we'll do this. If you calculate it from scratch, it looks something like this. You have the 1 kilogram mass that's on the y-axis times 2.475 meters squared, plus you have the 1 kilogram mass that is on the other side of your axis, and that is at about 0.825 meters away from the axis through the center of mass. And the same thing is true for the 2 kilogram mass. They're both 0.825 meters away from the axis through the center of mass. And if you crank that calculation through, you discover you get exactly the same answer, which you should. So it's a good way to check your answer. You get, again, exactly 8.17 kilogram meter squared. Okay, so that's how you would do the math for that problem. Sorry that my document camera wasn't working. Like I said, I will write this one up a bit more neatly for you to see, so you can go over it and see how that works. I think we're going to stop there unless anybody has any questions about that. And thank you, Laura, for answering questions about angular velocity and angular acceleration and the directions of them. So I'm going to stop our recording now.